Hello everyone. Welcome to our lecture on analog electronic technology. After studying the operating principle, output characteristics, and transfer characteristics of field effect transistors, today we will learn the composition, operating principle, and circuit characteristics of field effect transistor amplifier circuits, as well as the general methods for analyzing their static and dynamic parameters. Please study attentively. We already know that when an MOS transistor operates in the constant current region, it can amplify signals by exploiting the control relationship between the gate-to-source voltage and the drain current. How do we ensure that the MOS transistor works in the constant current region? How is the signal input? How is it amplified? How is it output? Which factors affect signal amplification? These and other questions are the ones we need to resolve when analyzing the circuit. Next, we will focus our study on these issues. How do we make an MOS transistor operate in the constant current region? Below, taking an N-channel enhancement mode MOS transistor as an example, we analyze the composition of the basic common source amplifier circuit. To operate the N-channel enhancement mode MOS transistor in the constant current region, two inequalities must be satisfied. The gate-to-source voltage must exceed the threshold voltage, and the drain-to-source voltage must exceed the difference between the gate-to-source voltage and the threshold voltage. Therefore, we connect a voltage source V sub GG between the gate and the source, with its voltage set so that V sub GS is greater than the threshold voltage V sub Tn. Next, we connect another voltage source V sub DD between the drain and the source, setting its voltage so that V sub DS is greater than V sub GS minus V sub Tn, thereby satisfying the operating conditions for the constant current region. How is the signal transmitted through the MOS transistor? The small AC signal V sub I to be amplified is inserted into the input loop formed by the gate and source, causing variations in the gate-to-source voltage. Then how do we extract the output signal? In the output circuit formed by the drain and source, if no current limiting resistor is added, the transistor can be damaged. Thus, we insert a resistor R sub D in series in the output loop. R sub D limits the current and converts changes in the drain current I sub D into voltage variations that are output between the drain and source. Of course, a load resistor R sub L can also be connected directly in series with the drain in place of R sub D, in which case the current flowing through the load is the output current I sub D. Since the source is the common terminal of both the input and output circuits and is defined as the circuit's zero potential, it is marked with a ground symbol. Because the source is the common electrode of the input and output circuits, this circuit configuration is called a common source amplifier. In the circuit shown, the DC voltage sources V sub GG and V sub DD are the working power supplies that ensure the MOS transistor operates normally, while the small AC signal V sub I is the input signal to be amplified. It should be noted that the gate-to-source voltage V sub GS equals the superposition of the DC voltage V sub GG and the AC signal V sub I, and since V sub I is usually much smaller than V sub GG, according to the control relationship of V sub GS on the drain current I sub D, and neglecting nonlinear effects, the drain current I sub D and the drain-to-source voltage V sub DS are also the sums of a DC component and an AC component. Operating principle of the basic common source amplifier circuit. Static and dynamic behavior of the amplifier circuit. Dividing the MOS transistor amplifier circuit into static and dynamic cases for analysis and discussion is an effective way to simplify a complex problem. Note that here we only perform qualitative analysis of the dynamic behavior, while quantitative analysis will be introduced in the next section. What, then, are the static and dynamic conditions? When the input signal is set to 0, that is, when the AC small signal voltage source is shorted, only the DC components remain in the circuit. This state is called the static or DC operating condition, and the voltage and current waveforms in the circuit are all DC. To emphasize the static state, we often add the letter Q to the subscripts of voltage and current variables. Thus, in the static condition, the MOS transistor's drain current and the voltages between its electrodes are represented by I sub dq, V sub gsq, and V sub dsq, respectively. The purpose of setting a static operating point is to ensure that the MOS transistor remains in the constant current region during signal amplification. If the static operating point is not set correctly, the signal cannot be amplified properly. If the input signal is not 0, the amplifier circuit's operating state is called dynamic, or the AC operating condition. The analysis method usually involves designing the static operating point through the DC path and designing the amplification parameters through the AC path. A path through which only DC current flows is called the DC path. When drawing the DC path of the circuit, the AC voltage signal source is set to 0, which is equivalent to a short circuit in the circuit. The remaining parts of the circuit through which DC current can flow constitute the DC path. If the circuit contains capacitive elements, they can be treated as open circuits in the DC path. A path through which only AC current flows is called the AC path. In the AC path, DC voltage sources are treated as shorts with respect to AC, and capacitive elements are generally treated as shorts in the AC path. Estimation of the amplifier circuit's static operating point. The static operating point of the amplifier circuit is estimated through the DC path, with the specific steps shown in the figure. First, draw the DC path. Then assume that the NMOS transistor operates in the constant current region. Under this assumption, the three equations shown in the figure can be written. When V sub GG, V sub DD, V sub T and K sub N curl R sub D are known, the Q point V sub GSQ, I sub DQ, V sub DSQ can be determined. It is essential to verify that the constant current region operating conditions are satisfied. V sub dsq must be greater than V sub gsq minus V sub tn, and the result must be positive. If the condition is not satisfied, the initial assumption is incorrect, and a new assumption must be made followed by a reanalysis of the circuit. If the device is operating in the ohmic region, the drain current is given by I sub D equals K sub N times 2 times the quantity V sub GS minus V sub Tn times V sub ds. Note, because circuit topologies differ, apart from the MOS transistor's characteristic equation, other circuit equations may vary. Dynamic operating conditions of the amplifier circuit. On the basis of the static condition, when the AC small signal V sub I is added, the total voltages and currents in the circuit are as shown in the figure. In these expressions, uppercase letters with uppercase subscripts denote DC quantities. Lowercase letters with lowercase subscripts denote AC quantities, and lowercase letters with uppercase subscripts denote total quantities. Assume that V sub I is a sine wave. Then the gate-to-source voltage V sub GS is the sum of the original DC voltage and a sine wave. And through the control of V sub GS on I sub D, the drain current also becomes the superposition of a DC component and a sine wave, because the output voltage V sub DS equals the voltage source V sub DD minus the voltage drop across resistor R sub D. V sub ds is also a DC component superimposed with a sine wave. However, the phase of the sine wave is inverted relative to the I sub d waveform. As long as the circuit parameters are chosen appropriately, the amplitude of the output waveform can exceed that of the input signal, thereby achieving signal amplification. In fact, from the constant current region characteristic equation, it can be seen that because I sub d and V sub gs have a quadratic relationship, I sub d is not a pure sine wave. However, when the signal amplitude is small, the transfer characteristic curve allows us to approximate the relationship between delta I sub d and delta V sub gs as linear through the transconductance Gm. Conventional schematic representation and main analysis methods of amplifier circuits. In electronic engineering, to make the circuit look cleaner and more intuitive, it is common to use the symbol for a DC voltage source connected to ground and to directly annotate node voltages with respect to ground. Moreover, for some ground terminals, the port voltage is only annotated on the non-grounded terminal, with the implicit assumption that this terminal is the positive pole of the port voltage. This drawing method is often called the conventional representation, and the signal source symbol can also be omitted to further simplify the input port. The main analysis methods for amplifier circuits are the graphical method and the small signal model analysis method. In the next section, we will focus on teaching the small signal model analysis method. Through the qualitative analysis above, we now understand how the signal is amplified. During this process, note the following key points. First, the MOS transistor must operate in the constant current region and have an appropriate static bias. Second, the signal is superimposed on the static operating point and conveyed to the output via the MOS transistor's control relationship. The signal is also referred to as an AC quantity or a variation. Third, the amplitude of the output signal is limited by the supply voltage of the output circuit. The DC power supplies are not only the prerequisite for the MOS transistor's normal operation but also the energy source for signal amplification. These are the key points of today's lesson. Thank you.